Welcome to another deep dive, everybody. Today we're going to be talking about problem solving. And to do that, we're going to be looking at some insights from George Polya's book, How to Solve It.
A book that I'm sure many of you have heard of, especially if you've, spent any time in the math world.
Absolutely, yeah.
Yeah.
I think a lot of people may have even had this book assigned to them in school.
Right.
But we're going to be going a little bit deeper than maybe what you would have encountered in a typical high school classroom or even a college classroom.
Right. So, thinking back, to 1956, Polya writes this book. And even back then, he points out that math was the least popular subject.
Yeah, and actually it's interesting because he observed this kind of cyclical pattern where, teachers who maybe didn't have the best experiences with math themselves end up teaching math.
Yeah.
And then maybe unintentionally kind of passing on that dislike or that fear of math to their students.
Right. They're teaching detestation of the subject.
Exactly. Yeah. So we're going to try to take a different approach here. We're going to be looking at Polya's ideas, not just as they apply to math, but also to any kind of problem that you might be facing in your life. We're trying to uncover his perspectives on the art and the science of problem solving. So this deep dive is going to be all about equipping you with those tools to tackle anything, whether it's, a big complex issue at work or just a simple everyday dilemma.
Yeah. So let's dive into that. One of the first things that Polya talks about is this idea that math really has two faces.
Mm-hmm.
So you have this, the rigorous science presented by Euclid. It's all about this, step-by-step deductive approach where you're just proving these theorems and it's very structured and logical.
Right. That's kind of the finished product, the beautifully written proof.
Exactly. But that's not the whole story.
Right.
The other face of mathematics is what Polya calls mathematics in the making.
Oh.
So this is about the experimental, inductive process of how you actually discover mathematical ideas.
So this is more about like the exploring, the guessing, the trying things out, and maybe even making mistakes.
Exactly.
And I think this is where a lot of people, this is where they kind of lose interest in math because they're only shown that final product.
Right. They're only shown that, the beautifully written proof.
Right. But they don't get to see the messy process of how someone got there.
Exactly. So what Polya really tries to emphasize is that, this second aspect, mathematics in statu nascendi, which is, just fancy Latin for in the state of being born.
Right.
This is actually critical to a deeper understanding.
Yeah, it's like you don't really understand something until you've wrestled with it, until you gotten your hands dirty with it and tried to figure it out yourself.
Exactly. So the takeaway here is, understanding is not just about seeing the answer. It's actually appreciating the journey of finding it.
Absolutely.
Mm-hmm.
So how do we get started on this journey?
So for Polya, understanding is really an active pursuit. And he famously said, to understand mathematics means to be able to do mathematics. And what does it mean to be doing mathematics? Well, in the first place, it means being able to solve mathematical problems.
Okay, so it's not enough to just, passively read about something or even just to memorize information.
Right. It's all about getting actively involved.
Yeah, you have to actually engage with it, grapple with those problems, and work through them yourself.
Exactly. And, Polya talks about, there's a real importance of empathy in teaching. And I think this can be applied directly to the way you learn anything complex. It's a paradoxical truth. To really teach math well, you also need to understand how someone might misunderstand it.
So you have to put yourself in the shoes of someone who's encountering this information for the first time and kind of anticipate the spots where they might get stuck, the misconceptions they might develop.
Exactly. And he uses some great examples, from J.E. Littlewood to illustrate this. So one example, Littlewood would often work with his feet up.
Right.
And so a lot of the ways that the coordinate axes were described didn't match his actual experience. Another one is a teacher might describe a closed curve and without actually drawing it, assume a certain orientation.
Yeah. And I can see how that could be confusing if you're a student, listening to the description and picturing it in a completely different way than the teacher's intending it.
Exactly.
So these examples really highlight just how easily our own assumptions can lead to these misunderstandings, even with concepts that we might think are really straightforward.
Right.
Kind of makes you think about like times in your own life where you've struggled to learn something. Were there any hidden assumptions there that maybe weren't explicitly stated or challenged?
Right. So, this brings us to what Polya considers to be a central part of problem solving, and that's devising a plan. And at the heart of this is finding a connection between the data, so what you already know, and the unknown, which is what you're trying to figure out.
So it's like building a bridge between what you have and what you're aiming for.
Exactly. And Polya, he offers some really great guiding questions that can help you to create this plan.
Okay.
So the first set, it focuses on tapping into your prior knowledge. So have you seen it before? Or have you seen the same problem in a slightly different form? Do you know a related problem? Do you know a theorem that could be useful?
So it's all about activating what you already know and looking for patterns or connections to things that you've encountered in the past.
Right. And then Polya shifts the focus to the objective. So look at the unknown and try to think of a familiar problem that has the same or a similar unknown.
Okay, so you're really homing in on what you're trying to achieve and then thinking back to situations where you've been successful with something comparable.
Right, and this leads to directly using those known problems. So here's a problem related to yours and solved before. Could you use it? Could you use its result? Could you use its method?
Okay, so you're not just trying to remember if you've seen something like it, you're actively thinking about how you could apply that past solution or that method.
Exactly. And sometimes just reframing the problem can help you make those connections. So could you restate the problem? Could you restate it still differently? Go back to definitions.
I like that. So even just expressing the problem in a new way or breaking it down to its most basic parts can open up a whole new perspective.
Exactly. And now when you're trying to guide someone through this process, it could be a teacher with a student or even you guiding yourself.
Right.
Polya emphasizes that you have to guide discreetly and naturally, really trying to see things from the other person's perspective.
So it's about understanding where they're at and their thinking and asking questions that will help them arrive at the answer themselves instead of just telling them the answer.
Exactly. He highlights the importance of repeatedly asking simple guiding questions. Things like, what is the unknown? What are the data? What is the condition?
Right.
These questions focus attention, and they really prompt specific mental actions for the person trying to solve the problem.
What I find so interesting is that Polya points out a lot of these helpful questions, suggestions. They're not some secret mathematical knowledge. They're really just based in common sense.
Right.
He uses the example of looking at the unknown and thinking of a similar, familiar problem. It's like when you feel hungry, you naturally think about familiar ways to get food.
Exactly. It's just taking that everyday logic and applying it to these more formal problems.
Right. And, he also stresses that problem solving is a skill. And it's like anything else, you develop it through practice.
Right.
Much like learning to swim, you first observe how others do it, and then you practice yourself. And teachers, they should be modeling this by asking themselves the same guiding questions that they ask their students.
So the focus should be on showing that thinking process, not just the solution.
Okay, now let's say you have worked through the problem and you've come up with the solution. Polya says you're not quite finished yet.
Right.
He says the step of looking back is absolutely essential.
Right. So you check your reasoning, you go through each step that you took,
Okay.
and ask yourself, can you check the argument?
So you're not just checking your work, you're really making sure that you understand why it's correct.
Exactly. And he says you should pay particular attention to what he calls the touchy points.
Right.
Those places in the solution where you were least certain or where you think errors might be more likely.
Okay, and looking last also means considering the bigger picture. So can you use the result or the method for some other problem?
So you're thinking about the broader applicability of what you've learned. Can these insights or techniques that you've gained be used in other situations?
Right, kind of like taking that knowledge and turning it into a tool that you can use again in the future.
Exactly. And he gives the example of finding the diagonal of a parallelepiped. Could that result or the method you used be used to help you find the distance from the center to one of its corners?
Okay, so that's a specific example, but it illustrates the principle of like trying to extract those generalizable insights that could apply to a whole range of problems.
Right, and that leads us to his discussion of analogy,
Right.
which he says is sort of similarity in the relations of the parts.
So similar objects, they might just share features, but analogous objects, they share relationships.
Right, and he gives the analogy between the sides of a rectangle and the faces of a rectangular parallelepiped. So just as a rectangle has four sides and relationships like parallelism and perpendicularity,
Right.
a parallelepiped has six faces with similar relationships.
Okay, so it's not just that they both have sides or faces, it's the way those sides or faces relate to each other.
Exactly.
And, analogies, it's everywhere, right? It's how we understand a lot of things in the world. It's in everyday language. It's in scientific discoveries.
Right.
And they can range from really loose analogies to incredibly precise ones.
Right.
Like in mathematics, there's this concept of isomorphism, which is essentially a perfect blueprint.
Mm.
So every part in the blueprint has a corresponding part in the actual structure.
Yeah.
And they're related in exactly the same way.
Right.
That's like the most precise form of analogy you can get.
Exactly. And Polya illustrates this power of analogy with this problem of finding the center of gravity.
Okay.
So if you know how to find the center of gravity for a triangle, that's a simpler analogous problem
Right.
that can give you a framework, maybe a set of steps or insights that you can use to then figure out how to find the center of gravity of a more complex shape like a tetrahedron.
So it's almost like building a smaller model to understand how the full-size machine operates. You're using the simpler problem as a guide to tackle the more complex one.
Exactly. And then Polya talks about auxiliary elements, which are basically new components that you bring in when you're thinking about the problem. And these can be anything from, drawing extra lines in a geometry problem to defining new variables in an algebra problem.
Right. It's like bringing in extra tools or lenses to help you see the problem in a new way.
Exactly. And he points out that a lot of times, going back to the basic definitions of the terms involved can reveal opportunities to introduce these helpful auxiliary elements.
Okay, so like if you're working with a problem that has a circle, you might explicitly think about its center and radius because those are essential to the very definition of a circle.
Exactly. And he gives this example of constructing a triangle when you're given one of its angles, the altitude and the perimeter. Working directly with that perimeter can be awkward, but if you consider the symmetry in the problem, with respect to the two unknown sides,
Right.
you see a much better way to incorporate that perimeter into your construction.
So the auxiliary elements are really about finding those strategic additions that can make the problem more solvable.
Right. And then there are also these auxiliary problems themselves.
Okay.
And these are problems that are related to your main problem, but they're simpler.
Okay.
And the hope is that if you can solve these auxiliary problems first, they'll give you some insight or a stepping stone to help you with the original, more difficult problem.
Okay, so it's almost like breaking down a big problem into smaller, more manageable chunks.
Right. And the benefit that you get from solving these auxiliary problems can be either in the result,
Okay.
Which you can use in your main problem, or in the method.
Right.
So the way you solve the auxiliary problem might be adaptable to the main problem. Polya gives this example of, finding the diagonal of a rectangle.
Right.
That might be a useful auxiliary problem if you're working on a more complex problem with a parallel pipette.
Okay, so you're looking for those connections, those transferable skills or insights that can bridge between the two problems.
Exactly. And of course, there's a trade-off with auxiliary problems because you're spending time and energy that you could be spending directly on the main problem.
Right.
But the potential rewards, making the problem easier or learning new techniques, often outweigh the costs.
And, we can't talk about problem solving without mentioning those moments of insight, those aha moments where the solution suddenly becomes clear.
Right, what Polya calls bright ideas.
Yeah, he describes it as this sudden restructuring of your previous understanding, like a completely new way of seeing the problem.
Exactly, and he uses the example of, someone in Aristotle's time observing the phases of the moon. And they had this bright idea that the moon's changing appearance was similar to how a ball illuminated from one side looks different from different angles.
And that completely revolutionized the understanding of the moon and the sun as being spherical bodies.
Yeah.
It's those flashes of insight that can really unlock a solution that just seemed completely impossible before.
Right, but even after you get that bright idea,
Yeah.
Polya, he emphasizes the importance of testing and checking your result.
Of course, you want to make absolutely sure that it's valid.
Exactly, and he points out how problems in letters, so, algebraic problems,
Right.
those are particularly good for testing through what he calls specialization.
Look.
And this means substituting specific values for the variables to see if that general solution holds true in these simpler cases.
Right, so it's like taking your abstract formula and plugging in real numbers to see if it actually works out in practice.
Exactly. And Polya reminds us that, our mathematical knowledge isn't just based on these formal proofs. Testing our results, even in informal ways, strengthens our understanding and gives us more confidence in the solution.
Absolutely. And once you have that solution that's been tested and checked, Polya urges us to ask, can you use the result?
Right, so you're looking for ways to apply that discovery.
Yeah, can the solution or the method be used in other problems, even ones that might seem quite different at first glance?
Right, and he gives this example of introducing and then eliminating rectangular coordinates as a way to simplify certain problems.
Okay, so it's like having a special tool in your toolkit that you know can come in handy in specific situations.
Exactly, and that leads us to the concept of generalization, which is basically going from a specific observation to a broader principle.
Right, like finding that underlying pattern that connects seemingly disparate things.
Exactly, and Polya illustrates this with the observation that the sum of the first few perfect cubes, so
Right.
one cube plus two cube, one cube plus two cube plus three cube, and so on, all happen to be perfect squares.
Interesting.
And that can lead to a general conjecture
Right.
about the sum of the first n cubes.
Okay.
And generalization can also be a strategy when you're stuck on a hard problem.
Okay.
He mentions this example of, finding a line that bisects the volume of a regular octahedron.
Okay.
That sounds really complex.
It does.
But if you generalize it to any solid that has a center of symmetry, the problem becomes way simpler.
Yeah, because then any plane that passes through the center would bisect the volume.
Exactly. And then, the technique of going from specific numbers to letters,
Right.
like going from a numerical problem to an algebraic formula,
Right.
that can also be super valuable for checking results and gaining deeper insights that can apply more broadly.
Okay, and along with generalization, there's also the importance of asking, have you seen it before?
Right.
If you can recognize a connection to a problem that you've solved before, especially if that solution was simple,
Right.
that can give you a huge head start compared to starting from scratch with a new auxiliary problem.
Exactly. You ask yourself, could you use it? Could you use its result? Could you use its method?
Okay, so it's about leveraging your past experiences to make the current problem more approachable.
Exactly. And throughout this entire process, you're relying on what Polya calls heuristic reasoning.
Okay, and heuristic reasoning, it's not about rigorous proofs yet.
Right.
It's more about those provisional, plausible ways of thinking that guide your search for a solution.
Exactly. It's like the scaffolding you put up before you build the solid structure.
You explore possibilities, make educated guesses, you follow promising leads, you don't have certainty yet.
And within this heuristic reasoning, there's a key tool, which is induction.
Right.
And that involves looking for patterns, finding those regularities in your observations to make those leaps towards a general principle.
Right, and he uses the example of the sum of consecutive cubes again. You can create a table of values.
Okay.
And it really suggests a general rule.
Okay.
And then you can go from that observation to a more precise mathematical formulation and through testing.
Right.
Whether it holds, when you go from n to n+1, you can actually arrive at a proof.
Okay, so you start with those specific examples, you notice the pattern, and then you use mathematical induction to kind of solidify that into a general rule.
Exactly. And in geometry, a useful strategy is to think about loci.
Loci.
Okay.
And loci, just to remind our listeners, that's basically the set of all points that satisfy some specific condition. Exactly, and a lot of times you can simplify a problem by thinking of it as finding the intersection of two or more of these loci.
Okay.
So, for example, you want to construct a point that's equidistant from two given points and also a certain distance from a line.
Okay.
Each of those conditions defines a locus.
Right.
And the point that you're looking for is where they intersect.
So it's like finding the point that satisfies all of the given conditions at the same time.
Exactly. And you can generalize this,
Right.
to solving problems by focusing on part of the given conditions
Right.
to find the locus of possible solutions.
Just think that's something that we do intuitively in a lot of situations, like even with a crossword puzzle.
Right.
If a clue says forward and backward part of a machine, you might think about, okay, what are all the words that could fit forward part? What are all the words that could fit backward part?
Right.
And then you're looking for that overlap, that intersection.
Exactly. And sometimes, when you're dealing with a really tough problem, the solution might be as simple as going back to definitions.
Back to the basics.
Right, especially when you have all these technical terms involved. And Polya illustrates this with the example of finding where a line intersects a parabola.
No way.
So if you go back to that definition of a parabola as the set of points that are equally distant from a point, the focus, and a line, the directrix,
Right.
you can rephrase the problem in a way that's much more solvable.
So it's about really understanding those core concepts and using them actively in your problem solving.
Exactly. And then as you're working toward a solution, Polya has this crucial reminder, did you use all the data?
Oh, that's a good one.
Right.
It's easy to get fixated on one part of the problem and completely overlook some crucial piece of information.
Exactly. He goes back to the parallel piped problem where a student might get the diagonal of one of the faces right, but then get stuck because they forget to use the information about the third
Like
dimension.
they haven't used all of the data that was given.
Right. So it's a prompt to check that your understanding is really complete.
Okay. And then Polya even acknowledges the role of guessing in problem solving.
Right.
Even if your guess is wrong, it can help you explore the problem and lead to more informed ideas later.
Exactly. He uses the example of someone guessing that a square has the biggest area among quadrilaterals with the same perimeter.
Okay.
And that actually leads to a simpler problem,
Right.
which is proving it for rectangles.
So even a wrong guess can be a stepping stone.
Right. And then when you're working with assumptions, Polya says it's fine to temporarily assume something's true as long as you don't then mistake that possibility for a certainty.
Yeah, it's like exploring a potential path without committing to it being the right one.
Exactly. He uses the analogy of a judge, considering a defendant guilty or innocent without jumping to conclusions.
Right. You have to keep an open mind and be willing to revise your assumptions as you learn more.
Exactly. And, with geometry problems, drawing a figure is often essential.
Yeah, but Polya cautions us to be thoughtful about how we draw that figure.
Right. Don't accidentally introduce assumptions.
Yeah, like assuming lines are equal or perpendicular when they're not explicitly stated to be so.
Right. He suggests a triangle with angles like 45, 60, and 75.
Yeah.
That's a good example of a general triangle. It doesn't suggest anything special about its sides or angles.
Right, so you're keeping it as open-ended as possible
Yeah.
to avoid making any unwarranted assumptions.
Exactly. And then Polya talks about two types of problems. Problems to find and problems to prove.
Okay, so problems to find, those are where you're trying to discover some unknown that satisfies certain given conditions.
Right.
And problems to prove, those are where you're trying to demonstrate whether a given statement is true or false.
Exactly.
Sure.
And then he talks about two powerful but sometimes counterintuitive methods of proof.
Okay.
Reductio ad absurdum and indirect proof.
Okay, so reductio ad absurdum, that's where you assume the opposite of what you're trying to prove, and then you show that that assumption leads to a contradiction.
Right. And he uses this puzzle, like writing down numbers with each digit used once
Yeah.
to sum to 100. You can show this leads to a contradiction.
Right, because the sum of the digits would have to be divisible by 9, and in that case, it wouldn't be.
Exactly. And then indirect proof, you start with an assumption, usually the opposite of what you're trying to prove.
Okay.
And you show that this assumption leads to a contradiction. The classic proof that there are infinitely many prime numbers is a good example of this.
Right, and it can be a bit uncomfortable to approach proofs this way,
Right.
but it can be a very effective technique.
Right. Polya also has these rules of style in teaching.
Uh-huh.
For style, have something to say and say it one thing at a time.
Right.
And for teaching, the first two rules are know what you're teaching and know a little bit more than what you're teaching.
Yeah, which really just highlights that, the teacher's own understanding and enthusiasm are so important.
Right. Another key skill is setting up equations.
Right, because a lot of problems, especially in math and science, they involve translating information from words into mathematical symbols.
And Polya describes this as a translation process.
Right, so it's not just about plugging in numbers. You really have to understand the problem deeply and be familiar with mathematical language to be able to express it correctly.
Exactly. And as you're working, there are signs of progress, these heuristic suggestions that can point you in the right direction.
Okay, so these are kind of like those little hints that you're on the right track.
Right. It might be a feeling or maybe a piece of information that previously seemed irrelevant now suddenly feels important.
Okay, and he gives the example of a chess problem where, maybe you're initially focused on certain pieces, but then suddenly this previously unimportant piece becomes crucial to the solution.
Right. And Polya reminds us that these signs, they're usually probable, not certain. He says, follow, but keep your eyes open, trust, but look.
So be open to revising your approach even if you feel like you're making progress.
Right. And sometimes you can gain insights by simplifying a problem and looking at special cases.
Okay.
He gives this example of two ships moving. And to find the shortest distance between them, you can simplify it by considering one of the ships to be at rest.
Okay, so you're basically making the problem easier to visualize and solve By focusing on a more specific scenario.
Right, and then there's the technique of working backwards, which is also known as analysis.
Right, so this is where you start with the desired outcome, and then you reason backwards to figure out how you would have gotten there.
Exactly, and a classic example of this is that puzzle of measuring out exactly 6 quarts of water when you only have a 9-quart container and a 4-quart container.
Yeah, and that could be a really effective way to solve these kind of step-by-step problems.
Right, and Polya also talks about this test by dimension, which is helpful in areas like physics and engineering.
Okay.
You analyze the units or the dimensions of the quantities to check if the formula is correct.
Okay, so if you're calculating an area, the answer should be in units of length squared.
Right, and if you're calculating a volume, it should be in units of length cubed.
And if your units don't match up, that's a clue that something's not right in your formula.
Exactly. And finally, Polya discusses variation of the problem.
Okay.
Which means, seeing how the solution or the problem itself changes when you tweak the conditions.
So it's about not just settling for one solution, but actively exploring the problem space to see what other insights you can glean.
Right, like changing numbers in a problem to letters.
Okay.
And seeing if your solution holds true.
So to wrap things up, we've covered a lot of ground here today.
We have.
But it's clear that Polya's book, How to Solve It, is just full of practical advice that goes way beyond math.
Yeah, it's really a guide to better thinking.
Absolutely. The key takeaways are that problem solving is an active process. It's about really understanding the problem, planning carefully, using what you already know, making connections, being okay with making mistakes, and then critically evaluating your solutions.
Right, and we really encourage you to use these principles in your own life, no matter how complex the challenges are.
And to leave you with something to think about, the next time you're facing a problem that just feels impossible, think about the nature of that difficulty. Is it a lack of connection? Is there a simpler case you could look at? Or maybe that brilliant idea is closer than you think. Think about which of Polya's techniques resonated with you and how you might use them in your own life.
Yeah, that's great.
All right, that's all for our deep dive today. Thanks for listening.
Thanks, everybody.